Hi, Cass. I hope you're all doing great and had a nice weekend. I spent most of mine binge watching Brooklyn Nine-Nine on Hulu. Hopefully you did something equally fun. We're going to take a look today at a brand new unit, right? We've basically wrapped up our equilibrium unit. But first, just a couple of quick class announcements. I'm in PowerPoint now, so you can see the announcements. You've got your equilibrium review project due this Friday, right? That's the video that you're gonna make with your group. If you didn't email me your group members, then I assigned you to a group, so make sure you check your email. Everyone should have a group. Please make sure you check your email and you're following up and you're communicating with your group members, right? It's really important that you are working together to complete the assignment. If you have any questions about the assignment, please comment on Google Classroom. I'm sure if you have a question, your classmates have the same question. And I look forward to seeing all of your videos on Friday. Also on Friday, we're gonna have our equilibrium and rates of reaction practice test, right? So we're done with this unit. If we were in normal school, this is when we would be having our real test. For now, I don't want anyone to be like super duper stressed. And so we're just gonna do a practice test. But at some point in the future, you are gonna have a test on these same topics. So it's good for you to treat the practice test like a real test and take it seriously. Cool. This video, the classwork for today is watching this video and then answering some questions on Edpuzzle. Presumably, if you're watching it, you already figured that out. If you're somehow watching it on YouTube and not on Edpuzzle, like make sure you go to Edpuzzle so you can like answer the questions and get credit. Also, today's homework is that there's a survey due tomorrow just about how the class is going. I just want to see like, is there anything I can do to help you out? I'm like brand new to using Google Classroom, so like possibly there's some like things that could be better there. Just let me know. I really want to hear from you. I want to know like how much work you have and how much time it's taking you and just so I can gauge how we're running the class. Cool. This question was your classwork from Friday's class. I just wanted to quickly go over this because this is going to hit on, it's a nice review of all the parts we've talked about in Le Chatelier's principle and equilibrium. So let's think about how each of these stresses would shift the equilibrium of this chemical reaction. If we increase the pressure on any chemical reaction, right, if you're squashing in a chemical reaction, the equation is going to shift to the side that has fewer moles, right? When you squash it together, the molecules basically kind of try to relieve that pressure by creating fewer moles of molecules. And so if you increase the pressure here, you're going to shift to the right. If you increase the volume, that's really the same as decreasing the pressure, right? If you increase the volume of a gas, you've decreased its pressure. That gives you more room that can easily be filled by more molecules of gas. And so that's going to shift to the side with more molecules of gas or more moles of gas. So that's going to shift you over to the left. If you increase the temperature, well, you have to know if the reaction is endo or exothermic. They tell us in the problem it's an exothermic reaction. So that really means that heat is a product over here. If you increase the temperature, the reaction is going to use up that heat, right? And so what it's going to do is CH3OH is going to react to make CO and 2H2, right? Because that's what uses up heat, right? When this reacts to make these two, it absorbs heat. When these two react to make this, it releases heat, right? It's exothermic. So the CH3OH is going to react to make more CO and more H2 in order to use up the extra energy that you've added. And so the equilibrium is going to shift to the left, right? For any exothermic reaction, if you increase the temperature, the equilibrium is going to shift to the left. If we increase the concentration of H2 is going to collide more with CO and make more of the products, and so your equilibrium is going to shift to the right. If you decrease the concentration of CH3OH, then there's going to be fewer of these molecules reacting to make these, and so the rate of the forward reaction is briefly going to be faster than the rate of the reverse reaction, and so you're going to make more of the products, right? And then eventually it'll balance out and the rates will be equal again and it'll re-achieve equilibrium, right? But so your equilibrium is going to shift to the right. Okay, and if you add a catalyst, that has no effect on equilibrium. That's going to speed up the forward reaction and the reverse reaction. They both get faster. They stay equal to each other, and so your equilibrium doesn't change. Cool. If you have any questions at all about any of the homework problems or the equilibrium problems we've gone over so far, please let me know. Again, your review video and your practice test are both going to be this week on Friday. Cool. And now on to something completely different. So I've pulled up a slide that has 6 different things, 6 different types of matter. I want you to take a minute and think about what these 6 things have in common. See if you can come up with anything that all 6 have in common, right? Humans, gasoline, coal, diamond, trees, and plastic. Cool. Every year someone is like, they're all solids. And we're like, no, gasoline is a liquid. They're not all solids. So that doesn't work. But they are all carbon-based, right? All 6 of these substances are really fundamentally structured by carbon atoms linking themselves together in different ways. And so it's worth noting that carbon is a really, really versatile, powerful element. You often hear it referred to as the element of life, because every living thing is based on carbon. All of its molecules are based on carbon. And carbon can create such a wide variety and diversity of living and non-living things because it's able to bond in so many different ways, right? And so you can get, gasoline, which is a flammable liquid. You can get diamond, which is like one of the hardest substances on earth, right? You can get trees and people who are like, living and doing all the things that living things do, growing and reproducing and all that, all from the same element, carbon. And that's important because that's what we're going to be talking about for the next couple of weeks. We're going to be talking about organic chemistry, which is the study of the chemistry of carbon. So for today, we're just going to do like a brief introduction. We're really going to get in deep on Wednesday. But I just wanted you to know why carbon is such an important element. So let's look at an example of how carbon is used to basically create life. So if you look at any living thing, right, any living thing has genetic information. One of the sort of characteristics is that living things reproduce, and we do that by basically copying our DNA. Now, one chromosome of DNA is basically built mostly out of carbon. There's other elements as well, and they're super important too. But the sort of basic building block of DNA is carbon. One chromosome has about 650 million carbon atoms. And for those of you who took biology last year, you might remember that the way DNA is structured, right, it's this double helix, right, you see the 2 chains, and in the double helix, there's these different base pairs, right, adenine, thymine, guanine, and cytosine, and they are paired, right, so anytime you have A, it's paired with T, anytime you have C, it's paired with G, et cetera, et cetera. And that's super important because it determines how DNA works. So here's a close-up of just one adenine and one thymine. And what you can see again is that each of these is a carbon-based molecule, right? The main element that's present in both of these is carbon. There's other elements here too, right? Hydrogen is very common in organic molecules. Organic molecules pretty much all have hydrogen. A lot of them also have nitrogen and oxygen. Those are some of the next most common elements in organic molecules. And so you can see that we've got this mixture of carbon, nitrogen, oxygen, and hydrogen. There's other elements that will show up in organic compounds as well. Some of the halides do, like fluorine, chlorine, bromine, iodine. And we'll talk about those a little bit later. But the main basis for any organic molecule is carbon and hydrogen. Cool. Let's think a little bit about how DNA works. Right. So you know that DNA has that classic double helix. I think you probably learned that in biology, and there's a reason for that. Right. The reason for that is the point of DNA is that it can be replicated. And so DNA can unfurl its double helix, and for each strand, you can basically build up a new strand of DNA that matches the previous strand, right? Which then allows you to duplicate the genetic information without losing any information, right? Because like every adenine that's over here was paired with a thymine over here. Well, this adenine will get paired with a new thymine, and this thymine will get paired with a new adenine. And so you end up with two identical molecules where you used to have just one molecule. And so that allows DNA to replicate in order for organisms to reproduce, which is super important. And it also allows DNA to like pass on information, right? You can convert DNA to RNA, and then you take RNA and turn that into proteins, and that'll like basically like tell your body what to do. Like that's how DNA controls what's going on in living organisms, right? And so this property of DNA that you have these two strands that are held together, but you can unzip them and reproduce them is sort of a key feature of how DNA works. And if we zoom in a little bit, we can actually now use what we've learned about chemistry this year to explain how that works. So if you zoom in here, we can see what happens when thymine and adenine are next to each other, and what happens when cytosine and guanine are next to each other. The two strands of DNA need to be held together pretty tightly, but not too tightly. They need to be able to be unzipped. And so they can't be bonded together with covalent bonds. Right? If the two DNA strands were bonded together with covalent bonds, they would be held together too strongly. You wouldn't be able to unzip it and reproduce the DNA. And so, it would be useless, right? But it also can't be held together too weakly, or the DNA will just fall apart, and that'll be a problem too. And so what's happening is we've got intermolecular forces between thymine and adenine and between cytosine and guanine. Take a minute to think about which intermolecular force is holding together all four of these molecules. So if you look, you can see that oxygen is now bonding, or is attracting, it's not bonding, it's attracting to hydrogen, which is bonded to this nitrogen. This nitrogen and hydrogen are bonded together and are attracting to nitrogen, right? This nitrogen and hydrogen are bonded together, they're attracting to this oxygen, right? We've got hydrogen bonded to nitrogen here, hydrogen bonded to nitrogen, right? That's hydrogen bonding, right? We're looking at examples where hydrogen is bonded to either fluorine, oxygen, or nitrogen. Right? In these cases, it's mostly nitrogen. So we've got hydrogens bonded to nitrogen. That's a superpolar bond. And then that hydrogen can also get attracted to another electronegative element, like nitrogen or like oxygen. And so all of these molecules are held together with hydrogen bonding, which we know is the strongest intermolecular force. So the strands of DNA are able to be unzipped when they're supposed to be unzipped, right? Because they're not being covalently bonded together. They're being held only with intermolecular forces, but they're held together pretty strongly because they're held together with hydrogen bonding, which is the strongest intermolecular force. And it's also worth noting, thymine and adenine, these two molecules, are perfectly designed so that they can exactly hydrogen bond with each other perfectly. They're perfectly aligned to have these two hydrogen bonds. And cytosine and guanine are perfectly aligned to have these three hydrogen bonds. And this is key as well, because it means that cytosine will always bond with, or not bond, but always be next to, always intermolecular force with guanine, right? Cytosine is always going to be next to guanine because they have this exact structure that allows them to basically fit together almost like two puzzle pieces, right? Thymine slots together perfectly with adenine. And so when you're, making a new strand of DNA, once you know one set of base pairs, the other set of base pairs will bond perfectly because it'll match up, right? If you have thymine here, like, and you've got a bunch of adenine and cytosine and guanine, like the adenine's the molecule that's going to actually line up perfectly and correctly hydrogen bond and be attracted. And so you get the replicability of DNA comes from this hydrogen bonding as well. That's what allows each base pair to have its partner, which then allows you to replicate the DNA without like losing information. So this is just a quick example of how chemistry can be used to understand what's happening in living organisms, right? We're gonna get a lot more, we're gonna start a lot smaller than DNA with its, millions and millions of carbon atoms. But it's really important to know why this is important, right? And when we're dealing with organic chemistry, we're dealing with the chemistry of life. We're dealing with the chemistry of living organisms, including you and me. Cool. One last quick thing that I wanted to just introduce you to is that in organic chemistry, we're often dealing with pretty big molecules compared to like, H2O or like a lot of the smaller molecules we've seen before now. And so you'll often see molecules written out as a structural formula. So these four chemicals right here, these are all examples of structural formulas. A structural formula is kind of halfway in between a chemical formula and a Lewis-Dot structure, right? A chemical formula just tells you which elements are in the molecule, right? A structural formula kind of hints at how those atoms are connected together. So CH3COOH kind of suggests, okay, we've got CH3 over here, then we've got another carbon, and then somehow we've got this like OOH business, right? And so it kind of gives you a hint about how the atoms are connected together, right? This structural formula is kind of telling us, okay, we've got a carbon with 3 hydrogens, then another carbon with 2 hydrogens, then another carbon with 2 hydrogens, then oxygen, then another carbon with 2 hydrogens, then a carbon with 3 hydrogens. Right? We can easily convert a structural formula back into a basic chemical formula by just combining all of the atoms that are the same type. So for example, for this first one, right, we can combine the 2 carbons, we can combine the hydrogens, and we can combine the oxygens, and we'll get C2H4O2. Generally, formulas are written carbon first, then hydrogen, then oxygen. You could write it like O2H4C2 or H4C2O2. Like, it doesn't matter. No one cares. It's the same thing. 6 of one, half a dozen of the other. Let's look at the next one. Take a minute for the next 3 and see if you can write the chemical formulas that go with these 3 structural formulas. So take a minute to see if you can do that yourself. Okay, so this next one, it looks like C5H12O, C2H7N, and C4H5Cl. So you can see that the structural formula actually gives you a lot more information than the chemical formula, right? If I just gave you this chemical formula, C5H12O, you would have no idea where the oxygen molecule, where the oxygen atom is inside that molecule, right? But if I give you the structural formula, you know exactly where it is, right? It's in between carbon number 3 and carbon number 4, right here. And so the structural formulas are very useful, and we use them a lot in organic chemistry. We're gonna, again, get into a lot more nitty-gritty details next time, but this was a nice overview of some of the most important ideas for organic chemistry.